Hello developers, let's continue developing. My name is Veko and we will be taking on the second part of the 23rd day of the 2022 Advent of Code. If you managed to go through the first part, that was a huge video, and this part will be much simpler and much easier. Fortunately, we get that the second part this year in general actually. If the first part is hard, the second part is gonna be real easy. Basically, most of the more of the same. In previous years, we had often cases when the first part was trivial, so to say, easy to do, and then the second part was kinda extremely hard. Basically, the first one was simulate 10 steps, the second will be what will be the result after 30 trillion steps or something like that, so we would need to somehow change our model or something like that. Or if the first part was execute this code on the machine you built, the second part will be, well, reverse engineer it so that you get this result. One of the previous days that I haven't solved, I think it's day 21. Yeah, this one is like that. So the first part is relatively easy, and I think that we will solve it quite easily. But the second part, I haven't seen it officially, but other people have told me that it's gonna be tricky, that we're gonna do a lot of reverse engineering. Anyway, not with this task. With this task, we basically need to continue simulating after the 10 steps are done until we get to a point when the elves are sufficiently far away from each other that they stop moving. When they stop moving, basically it means that each elf has no immediate neighbors. So they are far enough away. They form some kind of a circle. Yeah. And what is the number of the first round when no elf moves? For our example, it should be 20. In the meantime, I did some refactoring of all of this. I didn't like that we have a lot lets, a lot of passing back and forth. So basically, I removed the elf map completely from outside. The elf map is just something that we are actually using while we are calculating the elves. Also, the ugly code with the next functions is removed. Now we have this kind of array of functions. We are calling them with a reduce, and this will either give us a coordinate or it will give us an undefined value. If it gives us the undefined value, then we're not changing. Otherwise, that's it. That's the value that we're gonna put. That part about the duplicates is more relatively the same, and we don't actually need the elf map to calculate the field, the size of the field. And since we're generating the elf map at the beginning, we don't need to calculate the maximums here. Here we will just calculate what is the maximum of the area, that's the area, and then we remove the elves, we get the result. So for the second part, it's totally the same and totally the same code. And as I've said before, I never want to have dependencies between the first one and the first part and the second part. And one other thing, then these next functions, which were kind of ugly and repetitive, I replaced them with a function generator. So this is a function that takes a direction and a transformation method and will return the next direction, which is also a function. So this is a function that returns another function. So using that generator, we are generating the four next north, next south, next east, next west functions. We could also use this maybe as transformators, but Actually, why not? So we're having a coordinate. Let's call the coordinate C, and then we can return get neighbors, which will return a map type of C north. Get me the north neighbor of C. Yeah, this will generate all the neighbors and then only get the south one, but we can always kind of hard code the neighbors, or I don't know, do something like that. Get neighbors of C and get me the east one. And get neighbors of C and give me the west one. Let's just check that we have the same results. Oh, the processing time is much bigger this time. Well, we are gonna we are gonna return it. We are gonna type it twice, but at least the processing time will be much. Actually, it's not that much of a difference. Half a millisecond, half a second, something like that. But anyway, let's leave it like this. So, I've told you multiple times that I don't want any dependencies between part 1 and part 2, so I can type them independently. So, more or less, I will get all this code and copy it once more for the second part, because let's run it again. Let's leave it some room to maybe deviate somehow. So, what is the difference for the second part? Let's run it once to see that we are actually getting the same value twice. Yes, so that part is okay. Let's change to the small input that runs in just a few milliseconds, and let's see what we need to change in the second part. Well, we're gonna need to count the rounds. So yeah, that part we're gonna need. We don't have a limit, which means that now the condition will be something else. And we're gonna need to increase the round here at the beginning of a round, because we are never gonna have half a round. It makes sense to do it here. And I will add a boolean while that will be true while the elves are moving. So the elves are while the elves are moving, run. And we're gonna add an assumption at the beginning of each round. Yeah, begin the round and set that we are not moving. That's it. We are not moving. Now we have two cases when we will be moving. We will be moving if no, we will not be moving. We will not be moving if each elf doesn't have any neighbors, or in this case, if the elf doesn't have any free space to move. We saw that with this guy here, who cannot move anywhere. But if we have this case, if this returns something that is true, basically if here next elf, yeah, if next elf is defined, if it's not undefined, then we are moving, and then moving becomes true. So we keep running until we are moving, and then we don't need to calculate anything, we just need to return the rounds, the round number. We could be off by one, I'm not sure, but let's see. Seems we're not. seems that we have moved for 20 rounds as was the yeah, as was the sample input. So let's take the huge input. And to be honest, this will take a while because for 10 rounds we had something like 600 milliseconds. So for 100 rounds we will have 6 seconds and so on. And let's see. Yeah, it is processing. Yeah, and my computer got slowish because of something. And it took us 12,000 milliseconds. That's 12 seconds total to get to 1,000 rounds. Let's see if that is the correct number. And that is the right answer. And we have our solution to day 23. So day 23 is done. We moved past the volcano into the grove, and that's great. And now, this is quite a huge number. So I feel that there might be a room for improvement. And I feel that a lot of the time will not only be spent in all the 4 cycles that we are running, but that we are generating the map. And we don't really need this map because we are using this map just to detect if there are elves nearby. We can maybe just keep a list of elves because we don't have that many elves and detect if some of them are close enough or not close enough. Let's add a bit of code. Let's just add a bit of logging that will say how far the elves are going. So let's print these two numbers because these are actually the dimension that we're using. Hopefully we will just have a list of lots of numbers. Yeah. So it's 80 by 80, 90 by 90, 100 by 100. I think we are going to have around 20,000 cells that we are copying over and over and over again. Yeah, might be printing the round number would have been a good idea along with these two numbers, but it is what it is. Yeah, so we got to a place when we have 144 times 142. That is 20,000 cells that we are copying on each and every round of the processing. We are generating a new make matrix that is that big because we don't have a nice way to just say initialize me a matrix. And that matrix basically is running a for loop on each of the rows and generating another array. And that is very much not the image of efficiency. So we could, in theory, optimize this quite a lot. We can have it running in something that I would guess less than a second or a few seconds at most. But it is running, it is producing the correct result. So for now, we can leave it as is. It is slowish, it is sluggish, it is a candidate for optimization, but when we run all our tasks, then we will determine which ones we want to optimize and by how much. So for now, that's all there is about task 22. See you soon with task 24 or one of the tasks that we missed in the meantime. Don't forget to comment and like, and talk to you tomorrow.